Welcome to the course on computer design of electrical machines. We will have a lecture 38 today on computer design and analysis. Method 1. Well, with the outline of presentation, we will start with the introduction, then procedure for solving finite element problem, then meta model based simulation optimization, then references. And coming to introduction, the approximate flux path calculations are essential for rapid, reasonable, accurate calculation for the electrical machine design, and the permeance of each cell is related directly to the geometrical constant of the machine, slot height, truth width, core depth, and so forth, and a good understanding of the relationship between the machine dimensions and their effect on the motor parameter. Typically, the resistance and inductance is essentially obtained. And another method of analysis which have now become automated to the point of being useful in machine design is the method of finite elements. The method offers improved accuracy and almost an unlimited flexibility in the geometrical shape, boundary condition, and material properties in different regions of the problem. So, the necessity of accurate model for the design and analysis of electrical machine has promoted the use of numerical models, and these models are based on Maxwell equations for determining electrical and magnetic fields in electrical machines. And due to the machine's geometrical structure complexity and nonlinearity in the magnetization curve of the motor steel laminations, the determination of analytical solution becomes difficult, and utilizing the modern analytical tools is crucial for organizations to ensure desired objective and reduce cost. So, simulation, one of the most widely used and potential technique for analyzing the complex system, represents real-time systems through computational models, and various simulation types exist in the literature, including the finite element, finite difference method, and discrete event simulations, among the others. And finite element analysis method provides an alternate approach to predict the performance of an electrical machines. In finite element analysis, the entire field problems domain is divided into elementary submodules, which are called finite element, and the field equations are applied to each submodule as shown here in the figure that you can see. I mean, from the body in xy plane in two axes, how the typically the elements can be really defined as a typical triangular grid showing element and nodes with the nodes of I, J, K, and then say typically small elements as a triangular element. So different elements virtually are used, like sometime triangular, sometime we have a trapezoidal, sometime we have rectangular. So different model. Here it is shown as a typically a triangular model. So requirement of a construction of triangles are that all the nodes are connected. A typical triangle IJK can be considered to prescribe a first order function to exist within the triangle, which a linear interpolation of the function values at nodes ijk, and it is useful to define this function as a equal to alpha 1 plus alpha 2x plus alpha 3x over any point within the triangle defined the nodes ijk, and it is apparent that in particular the vector potential at the three nodes ijk must therefore be equal to ai equal to alpha 1 plus alpha 2xi plus alpha 3yi, and aj equal to alpha 1 plus alpha 2xj plus alpha 3yj, and ak equal to alpha 1 plus alpha 2xk plus alpha 3yk. For a two-dimensional magnetostatic problem, the vector potential concept is a useful approach that reduces the number of unknown functions from 2 bx and by to 1 as az, and from the property of the material we can say b equal to mu r mu 0 h, where h is the field intensity, b is the magnetic flux density, mu r is the relative permeability, and mu 0 is the permeability of free space, and the magnetic vector potential A having a dimensions of Weber per meter, which satisfy the relation B equal to delta into A, and the significance of A can be illustrated by considering the magnetic flux crossing the surface H, and from Gauss law, your phi s equal to surface integral S to B into ds. So, a suite of methodology and tools is available to aid designers in generating a geometrical representation of the artifacts for designing, dimensioning, and analysis, and finite element analysis anticipates how a product responds to a real world forces such as vibration, heat, fluid flow, and other physical effects. Through finite element analysis, it can be determined whether a product will fracture, deteriorate, or function is intended. So, during the product development phase, FEA simulation predict the performance of a product under real-world conditions, ensuring it can safely and effectively fulfill its intended task. And from equation 2 and 3, we can say phi s equal to surface integral delta into A into ds, and applying a Stokes theorem. So, is phi s becomes a surface integral delta into A into ds, and that is line integral L A into dl, and where A equal to Az as a function of xy into uz, where the line integral is along path L, which encloses S, and in two-dimensional case A has only the z component. So, if one lets Az equal to as a function of xy equal to A for two-dimensional case, then Bx equal to partial derivative of A with respect to y, and By equal to partial derivative of A minus partial derivative of A with respect to x. So, now coming to the procedure of solving finite element problem. So, considering typically an example of a single iron core inductor with an air gap as shown in the typically the figure, with the example of iron core inductor with an air gap as shown in the figure. So, assume that the dimensions of an inductor with zero gap are 6 into 6 into 1, and the core is wound with the copper such that the current density over the window is 1000 ampere per inch square, and the typically return portion of the coil is located opposite the movable iron keeper, and the magnetic field is to be determined for a half-inch air gap. Now, coming to as a typically step 1 for generating the mass, the total number of the triangular elements and their location must be chosen. In general, the elements should be chosen such that they are denser where the field is denser, and that is the particular important in the gap region. If the nonlinear iron is used, a typical triangular grid is shown here in the figure with the typically triangle with the numbers. So, triangular grid corresponding to the iron core inductor. Now, coming to step 2, the number of triangular elements and nodes. A triangular elements are numbered in consistent manner, so a numbering of vertices now take place, and for each element 3 nodal numbers are assigned. The numbering of the vertices will follow a zigzag pattern to keep the coupling between the elements banded around the typically the major diagonal, and the numbers corresponding to each element must be stored in the computer in consistent clockwise or counterclockwise manner. Now, coming to step 3, calculate the coordinates and area of each element. So, each triangular element is assigned the following attributes in computer array. First, the vertex number order counterclockwise, second x and y coordinate of each of the 3 vertices, and 3 the area of element calculated immediately before solution since it remains constant, and 4 a number identifying the material within the element, magnetic or non-magnetic, or what type if magnetic, and 5 the current density within the element as considering a constant. Now, coming to step 4, define the boundary condition. So, boundary conditions are now defined serving to establish the limits over which the problem will be solved, and in the example the outer surface of the inductor is defined to be 0 potential. It should be noted, however, that this constraint imposes serious limitations on the solution, namely that the flux lines are prohibited from the extending from the outer surface of the inductor, so that fringing near the air gap. Also, the leakage flux emanating from the copper region outside the inductor iron is neglected. Now, coming to step 5, the step of matrix S and T. So, S and T matrices are now constructed using the information in the array of step 3, and matrices are made taking the effect of one triangular element at a time. So, in general, for a simpler structure as shown in the figure, for the convenience, designation of nodes number 1 to 3 etc. has been used rather than ijk etc. for each of the triangle. The method of finite elements involved solving a three-dimensional set of equations in the form of, you can see the simple triangular grid having the finite nodes and 3 triangle with the element of 1 to 3, and the node ijk that is equal to 1 to 3 and 1 3 4 and 1 4 5, and with the matrix of course sij sik, the ij sjj sjk and ski skj and skk multiplied aijk ai aj ak equal to j delta by 3 as a unit matrix, and or is called S into A equal to T. So the quantity J delta is clearly equal to the current I passing through the triangular under the consideration, and delta is equal to the area of the triangle defined by nodes I, J, K. Now coming to step 6, solution of equation. So first S into A equal to T is solved by nodal potential A, and second flux density of each element is calculated typically from S and T to A and then B, and of course where the P equal to H upon B, and then from B it again goes to the loop. The flow chart for the solution of nonlinear finite element matrix equation given in the. So third, the relativity of each element is calculated from the scope approximately appropriate material BH characteristic. Fourth, the relativity are all updated, and fifth, S matrix is recomputed. Now coming to step 7, the plot of the field. Since line of the flux corresponding to lines of constant vector potential, the maximum and minimum values of vector potential are recorded, and for each element, fronts along each side are located, which are integral multiple of delta A, and points of equal potential on each of the two sides are connected by a straight line as shown in the figure. So when this procedure is repeated for all the elements, a flux plot having a desired number of equipotential lines results, as you can see in the figure. So showing the here typically connected equipotential lines on the boundary of the triangular element as defined as all in terms again AI, AJ, AK in terms of alpha 1, alpha 2, and XJ, and alpha 3 and Y typically IJK. Now coming to step 8, determinants of learned parameter value. So using a vector potential, number of flux lines per unit depth passing so any surface can be determined. As you can see the finished flux plot for the iron core inductor with an example. Now coming to introduction to finite element methods. So finite element uh, method magnetics is open source package, which is a collection of software programs designed to solve low frequency electromagnetic problem on two-dimensional planar and domains, and the capability of the program include addressing linear nonlinear magnetostatic problems, linear nonlinear third harmonic magnetic problems, linear electrostatic problems, and steady state heat flow problem. So Lua is the script engine used in finite element magnetics and typically available at the website. In order to analyze the problem, the preprocessor mode of import and of the DXP import export can be used as FEMM, support interfacing of the CAD program and finite element package. Generally, DXF import is the useful feature that allows the user to draw an initial geometry using their desired practical CAD package. And once the geometry is laid out, the geometry can be imported into FEMM and detail of the material properties and boundary condition. So you can say typically how the machine model looks in FEMM. So now coming to magnetic preprocessor for drawing a problem geometry, defining its material property and boundary condition. The magnetic preprocessor is used, and drawing a geometry usually consists of four tasks: drawing the endpoints of the line and arc segment that make up a line, and connecting the endpoints with either line segments or arc segment, and adding block level makers into the section of the model to define material property and the mesh sizing of each section, and specifying the boundary condition on the outer edge of the geometry. So typically you can say how this FEMM model of the BLDC motor looks like, typically in the ground in this figure. And now coming to magnetic post processor, the magnetic post processing functionality of a FEMM is used to view solutions generated by the F current solver, and a magnetic post processor window can be opened either by loading some previous run analysis via file menu on the main menu, or by pressing the magnifying icon from preprocessor window to view a newly generated solution. And magnetic post processor data file stored on disk have the .ans extension. You can see here how the typically field distribution in FEMM model of the BLDC look like. Now coming to the steps of finite element problems are preprocessing, preparing the field problems using the editor FEMM.exe mesh, subdivision of the domain in small elements using a triangle.exe, and solution of the field problem using fkn.exe, and post processing analysis of field solution, and computation of integral quantity using the editing PAM view.exe. Now in 2D FE, 2D in a 2D field problem, current density as J as a function of 0 Jz and vector potential A equal to 0 Az, and magnetic field strength H as a function of Hx x y 0, and flux density is B equal to Bx and By 0, and here it is a typically a PM section in the xy plane, as you can see in the figure. Now pre-processing steps are drawing the structure, point segments, arc, include the structure drawing of stator, air gap and rotor. So typical example of how the typically of stator slot, you start with the point, then line, and then you have a arc. Now pre-processing steps is marking the block labels and groups, and labels typically to give a name to the block, to assign the material property, e.g. the electrical conductivity and the relative magnetic permeability, to assign a current density to the block, and groups, all the stationary components are labeled in the same group, and the rotary R group in another with a label and material used typically like hair copper, then Fe iron, and then permanganate and air. Then the boundary condition, a boundary condition Az equal to 0 is defined in the problem, and the external lines are selected, and the boundary condition is assigned. Typically here you can see Z equal to 0. So boundary condition assigned along with the outer periphery of the stator. The material of the object can be defined on selected from a given material library, and the appropriate material is assigned to the object for the consideration of PM motor. Example, so Fe is assigned to stator and rotor laminations, and Cu is assigned to a stator slot, and NdFe is assigned, NdFeB is assigned to the rotor permanganate, and air is assigned to the air spaces. So now another factor is to provide the excitation to the system. Here stator currents are defined as circuit, and the ideal current source connected to one of the more block as shown in the figure. So I slot 1 is the typically current source connected to first slot, and I slot 2 is the current source connected to second slot, and I slot 3 the current source connected to the third slot, and typically so on, as shown in the typically the here in the figure as external circuit as excitation to the motor stator coil. Now coming to typically finite element magnetic on the basis of octave FEMM. So octave FEM is a MATLAB tool that allows for the operation of FEM by a set of MATLAB functions. So the toolbox work as a with octave MATLAB clone. When octave FM start using FEM process, the usual FEM user interface is displayed and is fully functional, and the user then has a choice of accompanying model analysis task either exclusively through the function implemented by the toolbox or by a combination of manual and programmatic operations, whichever is easiest for the task at hand. And the syntax of the Octave FM tool closely mirrors that of FEM existing Lua script language interface associated with the FEM version 4.2. And here typically is the process of interlinking with the MATLAB. So you have MATLAB program Lua script, and it goes to the model file, then result file, and come back to MATLAB function, which goes to final Excel file. Now coming to meta model based on simulation optimization. So engineering design is concerned with the making of decision based on the analysis which directly impact the product of service being designed. To accomplish this, the engineers typically engage in a great deal of analysis to understand the background to their decision, and it is often necessary for months of analysis by dedicated teams to be undertaken to inform key product decision. And the use of meta models, surrogate models, is to augment the results coming from a single expensive simulation code that needs to be run for a range of possible inputs dictated by some design strategy, perhaps a planned series of runs or those suggested by some such process. So the basic idea is for the meta model to act as a curve fit to the available data so that the results may be predicted without resource to use the primary source, the typically expensive simulation code. And the approach is based on the assumptions that once built, the meta model will be many orders of magnitude faster than the primary source, while still being useful, accurate, while predicting away from the known data point. Now there are two key requirement here. First is the significant speed increase in use, and second is the useful accuracy. So the clearly these factors are often in tension with each other, and the designer will often have to balance these competing needs carefully. And first, some form of data set relating to a series of input and output is obtained, and typically by sampling the design decision space, making use of the available and often expensive analysis code, and following this a suitable surrogate model that must be selected and fitted to the available data. So, since the initial design selections made to produce the first set of data will almost invariably miss certain features of the landscape, and the construction of a useful meta model often requires further judicially selected calls to the analysis code, and these additions call are termed infill points, and the process analyzing them is edge updating. And the basic steps of meta modeling process are illustrated in the flowchart in the figure on the next. So, the typically here it is a meta modeling process with the flowchart, sampling plan, define equipment, observation, quantitative evaluation of the design on your computer simulation, typically physical equipment, and construct surrogates, design sensitive analysis, then multiple fidelity, and then optimize or visualize, and typically as a yes, then visualization to help compressive design and escape, and then search infill criteria optimization using the surrogate and constraint present noise in data and and then go add new designs and then go into the iterative manner. Now coming to sampling of data, the design problems require the construction of a meta model that emulates the expensive response F, and Fx is the sum continuous quantity, cost, or performance matrix of a product or process defined by a k vector of design variables. X belong to D and eta Rk, and D as the design space or design domain. F is the for discrete observation or samples, and the task is to use this sparse set of samples to construct an approximation F dash, which can be then used to make achieve performance prediction for any design X belongs to D. And classical design include full factorial and fractional factorial design. The most straightforward way of sampling a design space uniformly is use a rectangular grids of points, and this is the full factorial sampling technique. And a special case of full factorial design is the 2k factorial design, which have k factors, where each factor has just two levels. And the full factorial design do require a large sample size as the number of factors and associated level increase. And for these reasons, full factorial design may allow you to estimate every possible interaction, although you are probably only interested in two-factor interaction or possibly three-factor interaction. Lastly, this design may not be the best approach when there is a strict limit on the number of test runs due to constraints such time, cost, resource, and number of factors and level and randomization. And here it is typically on the sampling of data. You can see example of 3 dimensions full factorial sampling plan. As you look into, and typically coming as a 2k factorial design follow a pattern that captures every possible combination of factor and level in design matrix. And this approach builds a model that estimates all of the main effects and each iteration. And table shows an example of 2k factorial design and of 3 factors, and each with 2 levels coded as low as a minus and high as a plus, typically with the run of 8 with ABC and plus with the plus minus. So, coming to typically replacing the code, the actual value of a specific test is straightforward. And for instance, if one of the factors is in the design is air gap length, that is variable varying from 0.35 millimeter to 0.55 millimeter, then the minus level will be 0.35 millimeter and plus sign will be of 0.55 millimeter. The order created using the systematic pattern shows above is the standard order, and this ordering scheme introduces one factor at a time and then combines with the factor preceding it. In practice, randomized text execution to ensure independent and guard against hidden factors, and failure to randomize many identity significant factor effects that are actually due to uncontrolled variables. The visual representation of the design space for 2 to the power 3k factorial design is a geometric cube where the test points are mapped to each corner of the cube, and figure provides a graphical representation of the cube with the codes -1 for the low setting and plus and 1 for the higher setting of each factor. As you can see here, the 2k, that k equal to 3 as a full factorial design with the 3-dimension space with different nodes typically here given in the cube. So if one of those factors are factors is insignificant, the design can collapse on the insignificant factor, and all 2k factorial designs are also orthogonal. Orthogonality means the model terms are uncorrelated with another and therefore estimated independently of each other, and this feature helps to determine whether factors affect the response, and without orthogonality the process of determining which factor truly contributing to the response is more complex. So the another sampling method is the Latin square and random Latin hypercubes. So if n designs are required and n by n square is built by filling the every column and the every line in a permutation of 1 to 3 up to n, and that is every number must only appear once in every column and every line. And for example, for n equal to 4 a Latin square, for this what such plans are usually known as look like this in the given in the typical matrix 2 1 3 4, similarly 3 2 4 1 and 1 4 2 3 and 4 3 1 2. So now coming to typically building a Latin hypercube, that is the multidimensional extension of Latin square, can be done in a similar way by splitting the design space into equal size hypercube like typically bins and placing the points in the bin one of each, making sure that from each occupied bin the design space can be excited along with direction parallel with any one of the axes without encountering any other occupied bins. As you can see, level 10 points Latin hypercube sampling plan here with the typically with the two axes x1 x3 and x2 x4 and x1 x2, and of course 3-dimensional with x1 x3 x. Now coming to another class of sampling plan that have generated some interest in recent decades are orthogonal way, and n to m matrix x with entries from a set of s greater than 2 symbols is called an orthogonal array of the strength r, size n with the m constraints and s levels in each of in if each n into r submatrix of the x contain all possible l into r row vectors with the same frequency lambda, and the number lambda is called the index of array, clearly n equal to lambda s to power r. So it is coming to the skinning, it is to minimize the number of design variables like x1, x2, xk before we attempt to model the objective function f, and the word scanning in the name of the design implies that they are intended to find factors with significant effect, and if we expect many variables to be inactive, a thorough scanning study has the potential to enhance the accuracy of subsequent model considering due to the reduced dimensionality, and it is however there is a reason to believe that most variables have a considerable impact on the objective, and it is advisable to focus efforts on the modeling itself. A great deal has been written about sampling plans and modeling methods, specifically aimed at input variable scanning, with the typically from Jones Tell of 1998. And the usual goal of the scanning design is to identify most important factors that affect process quality, and after scanning experiment usually do optimization experiment that provide more detail on the relationship among the most important factor and response variables, and the following designs are used for scanning: the two-level fractional factorial designs and Plackett-Berman designs, and of course definitive scanning design. Now, our typically on this scanning, our choice of scanning design depends on many different consideration, and many considerations are specific to the process such as number of factors to study, type of terms, typically linear interaction term, and etc., and number of the levels. As you can see, number of factors in mini tab for the common scanning of the design as shown in the figure. Now coming to constructing a meta model. So stage 1 is the preparing the data and choosing the model approach. So first step is the identification through a small number of observation of the input that have a significant impact on f, and the second step was to recruit n of these k factors into list x as a function of x1 x2 transpose such that this represents as a design space as thoroughly as possible, and after the selection of sample points optimization or training of the model parameter is to be done. So although several machines learning or regression technique have been developed for model construction, there has been little work on how to select the appropriate model for a particular application. Now coming to stage 2, typically for the parameter estimation and training. So maximum likelihood estimation is a method that determines the values of parameter of a model. Then the parameter values are found such that they maximize the likelihood that the process described by the model produce the data that were actually observed, and given a set of parameters w and the model f as a function of xw, one can compute the probability of the data set typically as function x1 y1 plus minus eta, or x2 y2 plus minus eta, or up to xn yn plus minus eta, having a resulted from f dash. And if we assume that the errors eta are independently randomly distributed according to normal distribution with the standard deviation sigma, the probability of the data set is equal to 1 upon 2 pi dt delta square power half n by half, and multiplication of I equal to 1 to n with exponential in bracket minus half in bracket y to as a power I minus f function f x w divided by sigma into chi square, and of course into eta. So now stage 2, typically the parameter estimation and training. So cross validation involves splitting the data randomly into q roughly equal subset, and then removing each of these subsets into turn and fitting the model to remaining an aggregated q minus 1 subset. And more formally, if the mapping eta, that is 1 to n, belongs to 1 to q, describe the allocation of the n training point to one of the q subsets, and f dash eta I is the value of attacks of the predictor obtained by removing the subset, that is the subset of which observation I belongs, and the cross validation measure which we employ here as a estimator of the prediction error is eta is cv as a function of w 1 upon n, and summation of I equal to 1 to n in bracket y to power I minus f to power eta I as a function of xi into w square. So now stage 3, typically the model testing. To test the model, we simply take a set of the test data of size nt and a set of predictions at the location of the test data and calculate error, typically RMSE. Now coming to polynomial regression model, let's consider the scalar valued function f observed according to the sampling plan x equal to x1, x2, xn, yielding the response y equal to y1, y2, n, and polynomial approximation of order of m can be written as f as a function of x, y, w equal to w0 plus w1x plus w2x square up to wm x power m, or equal to I equal to summation of m wi and xi x power I. Now this is typically here the MATLAB static software provides a number of different types of regression analysis, and choosing the correct type depends on the characteristic of your data. And this is typically the options available for the regression analysis for the skinny data, and this is the post-processing response of regression analysis. So now coming to response surface model. So the purpose of response surface models RSM is to optimize the process or system. So RSM is a way to explore the effect of operating condition, the factors on the response variable, and RSM is a tool which describe how we should run sequential sets of experiment, and this concept or design of experiment is different that of changing one variable at a time, that called C cost, as it leads to suboptimal solution. And the difference is that here the sequential experiments are conducted by changing the multiple factors simultaneously and not changing only one factor at a time. So now a box Wilson centric composite design, commonly called a central composite design CCD, contains an implemented factorial or fractional factorial design with a central point that is augmented with a group of star points that allow estimation of curvature. And if the distance from the center of design is placed to factorial point is plus minus 1 unit for each factor, the discrete from the center of the design is placed to a star point is absolute of alpha greater than 1, and the precise value of alpha depends on certain property desired for the design and on the number of factors involved. So here is the typically in the figures the central composite design CCD for the rotability on the left side and face a center typically and design on the right side. So here typically to note the central composite design CCD with axial points at the face is known as a face centered central composite design or the face central cube if the axial points are placed at the face. Now typically with this response model, CCD based model is an integral part of the response surface model technique, and the addition of the axial points to design increases model accuracy when it comes to building a second order quadratic model. And for 2 to power 3 design, the 2 level and 3 factors, the axial points are set from the center by alpha, and the value of alpha is chosen based on the number of factors. And for 3 factor design, alpha cube root 3 square root 3 with a 6 cube points and one added center point, and 3 levels are considered for 3 factor within the boundary condition, and the experiments are performed for different combination, and that is a total of 13 sampling required for a 2 level and 3 factor problem. And once the definite number of samples data is collected using CCD approach, the RSM model is evaluated. So the Box-Bachmann design BBD is an independent quadratic design in that it does not contain an embedded factorial or fractional factorial design. And in this design, the treatment combination are at the midpoints of the edges of the process space and at the center, and these designs are rotable or near rotable and require 3 levels of each factor, and the designs have limited capability of orthogonal blocking compared to the central composite design. And here is a typically in the figures representations of Box-Bachmann designs for RSM. Now these are the typical references which are considered to develop this material, and you can have a look on typical for this, and thank you very much.